DC motor Hopkinson tests. DC motor Hopkinson test. It's also called regenerative. Regenerative or back to back. Back to back. So in this method, a full load test is carried on two shunt machines, perfectly identical, that are mechanically coupled, perfectly identical, but are mechanically coupled, but electrically adjusted, such that one runs as a motor, and the other as a generator. Another line, the machine is the machines are started as unloaded motor. And with the fields adjusted, such that the one with the higher field current, is the generator. And the lower is the motor. The lower one is the motor. Test setup. So we start with if this is the motor, then the other one is the what? Generator, right? This is mislinked. is linked. So please get this. We have the applied voltage V, and then it gives a current in. I want to call it current I1. Let me give it an ammeter. All this I'm drawing like this are ammeter. This is ammeter 1. This is ammeter 2. So it will link, ammeter 2 will link I2. So we start this thing as unloaded motor, right? And therefore I1 coming through that. But you see, we are saying these are two perfectly identical machines. They are neither motors or generators. They are just perfect identical what? So once we started the first one as unloaded motor, and since they are directly coupled mechanically, while the motor starts to rotate, it will rotate the what? The generator, right? Yeah? So when it rotates the generator will produce a current, right? And this current will feed back to the system. Yeah? So we get, I want to give the current, so we have the current 1, current 2, and then this is the current getting to the motor. This is I4, let me give it I4. This is I what? I3, ammeter 3 to the field of the motor. So as you start this at a loaded motor, the motor will rotate. As the motor rotates, since they are coupled mechanically on the shaft, this will rotate the generator. The generator will generate power. This power that is generated is fed back into the system. So what do you expect here? How much current are getting here? I1 plus I what? Right? Because it's the current from the supply plus the current from the generator. They are all getting into the system now. Right? And the system continue like that. So this is the setup that we use. There's I4 in that case. This is what we call the mechanical coupler. Now, there are two stages we want to do the theory for this. Case 1, when we assume that both machines have the same efficiency. So case 1, both machines have equal, is equal the same as the same efficiency. Both machines have the same. This is A. Both machines have the same efficiency. Now, we want to take each machine. So let's start with the generator, the motor. So what will the motor input? Just look from here. Input means the power that's getting here plus the total current getting to the system, right? So what is the total current getting to the system? It is I1 plus I2. So what will be the power getting into the motor system? It will be V into I1 plus I what? I2. That's the power getting into the motor system. True? Yeah? V times the current getting to the motor system. And in generator, we talk of the generator output. So what is the generator output? So this equation 1, generator output. Generator output is equal to VI2. That is the voltage. These things are in parallel. In parallel, the voltage is the same. So it is VI2 is the generated output. This is equation 2. This is aside. I want to revise something in your mind. We know that efficiency is equal to P out over P what? Right? So what is P out? P out is equal to efficiency times P in. True. True. And therefore that's the concept we want to use here to get to what we call the expression we need to derive. So if we agree with this, then we can say what will be the generator motor output. Remember we have the motor input, right? Yeah? So what will the motor, if you fail to see from where you are, please make noise. Motor output. Motor output. In that reference. Motor output will be efficiency times the P in. Which is what? Which is efficiency times V into I1 plus I2. True? Yeah? Because this is the input. Right? So if this is the input, you are saying is efficiency times the input, we get the output according to that concept. But look here. The motor output is the input to the generator. True? Because it's the one that starts the generator here. Right? The output that you get from the motor is the input to the generator. So what are we saying? What is the generator input? Generator inputs is equal to motor output. Right? And therefore in that reference we can still say it is efficiency V into I1 plus I what? I2. Right? Taking the same case, what will be the generator output? So generator output is equal to the input, the efficiency times the input. So what are we saying? This is efficiency times efficiency V into I1 plus I what? Are we getting that point? If you have a problem, please raise before I move far. Yes. I'm going back to the diagram. We are saying the motor, we start the machine as an unloaded motor. When it starts to rotate, the shafts are linked like this, right? So we expect that as this thing rotates, it rotates the generator. And therefore, generator, so long as it rotates, it produces the EMF, right? So therefore, I'm saying the output to the motor is the input to the what? To the generator. And therefore, we are going to our equations. We realize the output of the motor is equal to the efficiency times V I1 plus I2. And therefore, if that is the input, that's the input. Therefore, we are saying, but output is always efficiency times the input of the same, right? And therefore, the input is efficiency V I1 V I2. So we have the efficiency squared because this is the input, right? So we have the efficiency squared V I1 I2. So what are we saying? We are saying efficiency squared V I1 plus I2 is the generator what? Generator output. This is equation, let me add more equations. This is equation 2, 3. and this is 4. So compare equation 2 and equation 4. What are they? They are generator outputs, right? Equation 2 and equation 4 all describe a generator what? Output. So we say compare equation 2 and 4. So we are saying efficiency squared V into I1 I2 is equal to V I2. Is that what we are saying? If you compare the two equations, right? You compare the two equations, that's what we are saying. And therefore, what is efficiency? Efficiency, let me have it square first, is equal to VI2 over V into I1 plus I2. So efficiency is equal to, without square is the root, see V na V itaenda, we cancel V and V, and therefore we have I1 over I1 plus I2. This is the equation that we are trying to drive. And an entire diploma, yeah, I2, thank you. Entire diploma, you can be told, prove that the same efficiency is given by I1 over I1 plus I2. That's the procedure. And then you can say note. However, this is not practical. This is not practical. Since the excitations and the armature current will not be the same. This is not practical since the excitations will not be the same. And therefore, what are we saying? We are saying let RA be the armature resistance, I3 generator field current, I4 motor field current, so look at let's start with the motor. I would wish to draw a table kind of. So what is the motor input? Just back where we are. It's V into I1 plus I what? I2, right? What is the motor field armature current? Motor armature current. Armature current is the current beyond this place. And therefore it will be I1 plus I2 minus I what? True? Yeah? That will be the armature current. And therefore the armature current is equal to I armature I1 I2 minus I4. So I want to get into the losses. Once we know that, we can do our losses. So the losses in the motor first one is armature copper loss, which is given by I1, I2, don't get tired, squared are what? Any armature current is given by the squared current of their resistance. Then we have the field copper loss. Field copper loss. Field copper loss is given by the voltage times the current of the field. So what is the field for motor? I4, right? So it is V I what? I4, right? If you want to have like armature copper drop, brass drop, we'll add it here, but we don't have it at this point. So we'll get hold of it when we get to example, right? So what is the total loss? Total loss for motor, it will be I1, I2, I4 squared array, which is what? Armature copper loss, right? Plus VI4, which is the field copper loss. We are done with the motor at that point. So we get back to what? Generator. In generator, we talk of generator output. What will be the output? VI2. Total is, I've added this plus this. Total losses. Oh. Total loss. So we have VI as the input. And now, what is the armature copper loss? Armature current from here. Generator armature current. Armature current. Armature current will be I2 plus I3. Yeah, because a current to a point is equal to a current leaving the point. This current of I, G, is coming from here. Yeah? So it's distributed into the field and the output. So we have I2 plus I3. So therefore, we can get the losses. The first loss is armature copper loss given by I2, I3 squared RA. Okay? Then we also have the field copper loss. Field copper loss given by V. What is the I of the field? I3. Yeah? The field is here. Right? I3. So the total loss is I2, I3 squared for the armature plus V I what? 3. Now, what is the total system loss? Remember, this system has both the motor and generator. So, what is the total system what? Loss. Total system loss is equal to motor loss plus generator loss. So what are we talking about? I1, I2, I4 squared array plus V I3, I4. I've done with the generator part, the motor part, right? Plus I2, I3 squared RA plus V I3. That will be the total system loss when we combine both the motor and the generator. What is the total system input? This system had an input from the source. What was the input? VI1. Right? That was what was supplied to the system. The others have been self-generated. So the system input, is equal to VI1. And therefore, the constant loss, WC, I'm fast, yeah? And therefore, the constant loss, WC, constant loss, WC is equal to system input minus system loss. Is it okay? Yeah? It's the system input minus system loss. What is the system input? VI1 minus, bring all of them, I1, I2, don't be somebody who gives up. The concept is so simple, the expression is too long. I3 plus I2, I4, I3 squared array plus I3. This is WC. But look at it. WC is the total for the system. We need for each machine. We need the WC for motor. We need the WC for generator. But remember, these machines were two identical, right? So we want to assume in the same case that the constant loss for each machine is equal to WC divided by what? Divided by 2. That's case 1. Is W. The whole of this procedure was to get WC. Right? So we have WC, the constant loss. So part case 1, efficiency as a motor. Efficiency as a what? We are still here. So you want to get efficiency as a what? As a motor. So motor, we know efficiency is equal to what? P in minus loss over P. Because the motor, you only know the input, you don't know the output. Right? You don't get you only know what you are supplying to the motor, you don't know what it's producing. So that's why we say the input minus loss over input. Now before I get there, we need to get our values. The motor input, continue repeating so that you get, the motor input is V, I1 plus I what? I2. Right? Losses, total losses, we have the armature copper loss given by I1 plus I2 minus I4 array. Then field copper loss given by V, I4. And finally, constant loss which is WC divided by 2. So what is the total loss? This looks like a count. Total loss is equal to I1, I2, I4 squared array plus V I4 plus W C divided by 2. Right? And therefore efficiency is equal to what according to this procedure? V I1 plus I2 minus total losses I1, I2 minus I4 squared array VI4 WC divided by 2 all over the input VI1 plus I2. Don't get out of this vehicle before we brake. And raise an alarm. Huh? We are landing. We have landed on a motor. B efficiency as generator. In a generator, we know efficiency is given by P out over P out plus what? Plus loss. Huh? That's in a generator. And therefore, in this case, we start with the P out. What is the P out? Power out in generator is V I what? I2. Losses, armature, copper loss given by what? I2, I3 squared array. Field copper loss V I3. Constant loss WC divided by what? 2. Total losses. Total loss I2, I3, RA plus V I3 WC divided by 2. So how do you get efficiency as a motor? V out, which is V I what? 2 over V I2 plus losses I2, I3 squared RA V I3 plus WC divided by 2 times 100. 100 is your choice. It's a means of communication. Huh? So that's all of HOPKINSON. Huh? It looks long, but concepts are very few. There are only 4 concepts. How many concepts? Only 4. Expression can be long, but there are only 4 concepts. That in concept 1 gets the WC. Then work as it as a generator efficiency and motor efficiency. Hata ni 3. There are only 3. Example. The HOPKINSON test. The HOPKINSON tests on two similar shunt machines gave the following full load data. Gave the following full load data. Line voltage 110, line current 48 amps, armature motor armature copper current 230, field currents, why we call them currents, is 3 amps and 3.5 amps respectively. Armature resistance for each machine is 0.035 ohms. Calculates the efficiency of each machine, assuming, there's another factor introduced here, assuming a brush contact drop of 1 volt per brush. So that's the case. You cannot do this without a diagram. You'll never be right. Because there are other factors that are not here. We are going to get them from the diagram. So we are saying we have 2 machines connected. So we have the voltage. What is the voltage? 110. So we have this as the motor. This will be the what? Generator. Please get it right here, then you can draw. Because if you don't miss this, you miss this, you are in trouble. So what are we given? What is the current coming in? 48. Right? Yes. What else are we given? Armature, motor, armature, current. Where is that? It's down here. 230. Field currents, we have 3 amps and 3.5, right? I told you in the initial statement that the one with a higher field is the generator. These are perfect machines that have only been electrically readjusted, right? So the higher field is the So we have this 3.5 going here and 3 going here, right? To the motor, right? So how much is coming down here? Yes, how much is coming down here? Up here. It is this plus this. Remember, they are dividing at this point, right? So it is 233. It's coming to the motor system. Out of this, 48 is given by supply. The rest is supplied by the generator. So how much is given by the generator? How much is given by generator? It is 233 minus 48. How much? 185. Coming from the generator. Down again, we are coming down here. Remember, 185 is the output, right? And again, the rest went to the field. So how much was the generator generating? 188.5. So until you do that, you cannot start to calculate on this thing. So have that. So you're ready to go? Right? So remember I said the first case is to get the constant loss, right? So we get back here and still this is my making, and I say this is motor, this is what? Generator. So what is the motor input? VI. We just say VI because we know the values by now. We don't say I1 plus I1. We know one value, right? So what is our VI? Our V is what? 110. Total current getting to the motor system? 233. Then I get back to the losses. The first loss is armature copper loss given by I squared R A, which is 230 squared times 0.035. I'm waiting for your calculator to work. I don't have one. How much? 25, yeah? 25,630. Then we get to field copper loss. Field copper loss, we agreed, is the voltage times the current of the field, right? Yeah? So that is 110, current to the field on the motor, 3. This one I can guess. What's the value here? 1851.5. So that's that. What else? We don't have any other. So we get the total motor loss, right? Total loss. There's one. The brush loss. The brush loss is given by voltage, by the current of the armature times the voltage drop. Are you getting that? Yeah? So each machine has how many brushes? 2. But we add 1 volt per brush. So how many voltage do you have? The current here is 230 of the armature and then 2 volts. Right? Are you getting that argument? This one is looking with a disbelief. We have brush 1 and brush 2. So each brush has a 1 volt. So for the motor, we have 2 volts drops on the brush, right? Times the armature current. This is for what? So the total loss, add all of them, 1,851.5 plus plus 330 plus 460. This is the total loss on the motor. $2641.5 watts. Once we do this, we move to the generator side. In generator, we are talking about generator output. So the output is given by V of the output. So what is that? 110. What was the output generator current? 185. This is the output. Yeah, the final one. So that's the generator output. Then we get losses. We have the armature copper loss given by the I of the armature and the armature resistance. What is the armature current? 188 squared times 0.035. Field copper loss given by V times the I of the field for the generator, 110 times 3.5. Then we have the brush loss given by the armature times the voltage drop. So we are talking about 188.5 times 2 volts. Hapa, let me start from here. Calculator? 20,350. Here? 12? 43.6. Hapa? Two? 385. Last? 28 point times 2? 377. So what is the total? Total loss is 1243.63 plus 385 plus 377. That is the generator total loss. Add all of them. 20.0563. So what is the system? The system loss. System loss is the motor plus generator loss, right? So we are talking about 20.05.63 plus 2641.5 total loss. Total loss 46, 47, 12, 13. What? This is the total system loss. And therefore, what is the system? Once we start with the system, you come to system again. What is system input? System input is VI1, right? So we are saying this is 110 times 48. This is the power getting into the system that was supplied. It's the 110 times the current getting in here, right? So that is system input. What do you get? 5280.
Yes.
So and therefore constant loss WC is the input, system input, minus system what? System loss. So 5280 minus 46 47 13. What do you get?
99.7.
Yeah? 99?
632.
Why do I suspect that's too big? 6? 87. Please check. Your figures are matched. So, what is the constant loss for each machine? That is WC divided by what? 2. So 632.87 divided by 2, 316.3544. So once we get WC, we can get the efficiency as a motor and efficiency as a what? As a generator. So, 1, efficiency as motor. So, what is the motor input? Input, we now have all the values. 20, 25, 630. Losses, we have the armature, copper loss, given by what? 1851.5. Field copper loss 330. Armature, this brass, brass loss 460. Constant loss. You now see why we were doing all that. Yeah? W what? C is given by 316.44. Total losses. Total loss. Add all of this. Add all that. From that total that we had, that is 2641 point that, add only 316.44, and you are there with the total loss. How much? 2857.94. So efficiency in a motor is given by P in minus loss over P in. So we are saying 25,630 minus it's one figure, 2857.94 all over 25,630 times 100. Efficiency as a what? as a motor.
Is that 28 or 29?
I have no calculator. Please confirm. Maybe calculator error.
57.9.
29?
I think it's 29 which are the problem. So it's okay with that.
Get the efficiency. B, efficiency as generator. Generator, we start with the generator output, which is VIL, that is 110. Well, I'm not getting to that, we have these values. 20, 350, losses, armature copper loss, which we got to be 1243.63. Field copper loss of 385. Brush drop loss 377. Constant loss WC is 316.44. Total losses, add all that, add to this. Where was that? Add to this 316. $20. Point? Efficiency as a motor is P out plus loss. So what are we saying? 20, 350 over 20, 350 plus 23. Somebody has not complained about 23. Is it correct? So what is the percentage here? That percentage should be a slight different, not a big one. Case 1, what percent? 0.5. And therefore case 2, very slight, not more than 3%. Yeah? Yeah? 89.8. So that's all about Hopkinson. Something you add, look at your camera, take the advantages and disadvantages of Hopkinson. Yes. I've only done stage 1. There's auxiliary and what you call external circuits with the field excluded. So I cannot add that now. So that will be the next. The next we will do Hopkinson tests with the field excluded. So that's a special case.